So we'll be discussing constraint motion today. So I'll be telling you various methods of solving, and the different approaches may appeal to different people. So whatever you find easiest, you can use that. So what's a constraint motion? In a constraint motion, one body is somehow linked to the other body. Say this body 1 linked to body 2. So if one body moves, like if I move 1 by a certain amount x this side, then this 2 is bound to move up by the same amount x if the string, black string, doesn't extend. It maintains the same length. So whatever is the length initially, say a plus the curved side plus b, so that much length remains same. So if it moves x this side, then this body has to go up by x. So here the mass of the body, whether this is 1 kg and this is 100 kgs or whatever, the mass of the body doesn't matter. It is the movement. If this body went down by say 2 centimeters, this body has to go on the other side by 2 centimeters. Plus we can see other constraints are also present. There is a ground. It cannot go into the ground. This one is going to go vertical because of gravity being vertical. So those constraints are there. So we are going to deal with questions where bodies are going straight up and down and horizontal. Then some questions where the bodies are going, where the rope in fact is going in an inclined direction. Questions where you have the rope going at an angle, and then some questions where you have one body on top of the other body, so particularly like a wedge, whatever. So these are on top of the other body. So we'll be discussing all these questions and various methods to approach them. So let's start with a very simple example first. Now let's take a very simple example of two masses overhanging from two sides of a pulley, and we have to find out that what's the ratio of the movement of this is to this. That means what is the ratio of the displacement of body 1, say moves by x, and this goes down by y. So what's the ratio of x is to y? Or say it had a velocity of v1, and then this one is say v2, or the ratio of acceleration a1 and a2. So whatever we find, whether we are going to find the ratio of the displacement or the velocity or the acceleration, the ratio is going to be the same, meaning to say x is to y is going to be your v1 is to v2 is going to be your a1 is to a2. The reason is in a certain amount of time, the distance covered by this will give you the velocity of the first mass, and in the same amount of time the distance covered by this will be y. So the speed would be given by x by a certain time divided by y by the same time. The reason is that if the body covers this distance x in a certain time, say t, then this body is going to go down by y in the same time t. So the velocity of this body will be x by t, and that the velocity of this body will be y by the same amount of time t. So if you want to go into instantaneous velocities and not average velocities, still the story will be same. You'll have dx by dt. We'll be studying the ratio of dx by dt, which is your v1, with dy by dt, which is your v2. Now the ratio of dx is to dy is going to tell you the ratio of the velocities also, and dx is a small movement of body 1x, and dy is a small movement of body 2y. So the ratio of dx and dy is going to be same as the ratio of the mega distance moved, which is your x, and this is your y, because all these dx added is ultimately going to be your x, and your all the dy's added is going to be your y. So it moves say a 0.01 millimeters up, and this one goes, like in this case it goes 0.01 millimeter down. Then every 0.1 millimeter up, it will create a 0.1 millimeter downward movement, and you add up all, and it becomes ultimately a 1 centimeter up, then this would be 1 centimeter down. So your dx is to dy ratio is same as your x is to y ratio, hence your velocity ratio is going to be same, and the speed gained, yeah, this is your v1, this is your v2, that ratio is going to be same. dv1 by dt is the ratio of your accelerations, that's your a1 is to a2, is again v1 is to v2 is same, so we have differentiated that, hence a1 is to a2 is also going to be the same. So sometimes they'll be giving you acceleration of 1 and they'll ask you acceleration of this, sometimes they'll give you velocity of 1 and ask you the velocity of this, sometimes they'll give you displacement and you have to find the displacement of this. All these cases the same constraint will be there. Now how to figure out that if it moves x up, then what would be this y quantity, how much will that be? Now to figure out that, one is just analyze the situation and have a physics brain working over here. If it goes by x up and the total length of the string can't change, then this string has to go down by y. So we can represent this in many formats. So one is a more mathematical one. We'll not prefer this later on. We'll do by intuition more than what I'm going to show you right now. We'll just see the total length of the string. So say this part length was equal to A, this part length was your B, and say you'll count the curve length also, which is actually not required because that curve length is going to come again. The part of the string will always be on the pulley, that much part. Say that is C. So what's the total length of the string? The length of the string L is equal to A plus B plus C. Now the length of the string is never going to change. Now we'll draw the new situation now. Let me clear this off first. Now what I'll do is I'll draw the new situation over here on the same diagram and not separately. So that's your new position of the blocks, and this orange string is now representing how they are held together. So what was your black string earlier is now your orange string. So we are just going to measure the length of the orange string. Now mind you, we know how much will be the movement and all, but still we'll say that this block from this where it held the block to where it is holding now, that distance moved. So this one has moved up by x, and 2 again from where it was holding the block to where it is holding the block, this block 2 has moved down by say y. Now we are going to count the total length of the string again. Now the total length of the string, now it's an orange string, so I'll write in orange. I hope it is visible. So total length of the string now will be this orange section. So how much is that? How much is this much? So your this part was A. So this is x less. So this part must be A minus x. So that's your this section. What about this section? What about this length? So from here to here was your B. Now you have y more. So this becomes B plus y. And this part remains the same. So need not count it in the initial length also, because this will always remain the same. So what you get is A minus x plus C remains as C, and you'll have this part as B plus y. Now this length and the earlier length was the same length, so we can equate the two equations, and what we get is A's will get cancelled, your B's will get cancelled, your C's will get cancelled, and ultimately what we get is 0 is equal to minus x plus y. In other terms, your y is equal to x. So that we already knew just by inspecting the situation. But this is what you are doing actually. You are ensuring that the whole string length is the same. So in this very simple question, you need not do it. And then in this simple question also, measuring all the lengths, all the parts was little cumbersome. It was tedious. So what we could have done is we could have, I'll redraw this. Yeah, so instead of measuring all the parts fully, that is a plus b plus c or a minus x plus c plus b minus y, what we can inspect is only the parts of the length of the string which is getting reduced and extended. So this part of the length got reduced by x, this part of the length got extended by y. The length of the string, we will imagine it is from the point on the pulley till wherever the block ends. Now the block is ending over here and this block is ending over here. So what we see is that this part of the length got reduced by x, and we'll write a minus x to the total length, which we are not mentioning by the way, and this part of the length got increased by y, so we'll mention it as plus y to the total length. So total length minus x plus y remains as the total length. Total length minus x plus y remains as the total length. So this total length need not be mentioned all the time, and we can write minus x plus y is equal to 0. The total length and total length is going to cancel off. So what we are going to get is y is equal to x. Now this is much faster than mentioning all the parts, and maybe more simple and lesser chance of you getting into an error. But you have to carefully inspect all the lengths of the string which can reduce, and this will work on a single string. If you have 2-3 strings attached, it's not the same string which is going along, then this concept you'll apply on each string separately. You can't apply it on all the strings. So this becomes a method of doing, but the preferred method over here was just inspecting. If you are too much into maths, you can write the length reduced and the length increased. If you have to be very sure of what is happening, you can count on all the lengths, but this diagram may become messy if there are more pulleys and blocks involved, which will eventually be the case. So let us study another case where you have a movable pulley. So here I'm not making a block just to make the thing simple. So what we are going to do is we are going to study the movement of this point 2 and the movement of point 1. So suppose we take it up by x, then how much is this going to move? So that is what we are going to study. So before I do it for you, just give it a go. You can redraw this diagram with the new position of the pulley, which is say here, and then the new position of the points, and do what has been told earlier to you. So now how to deal with it? So what do you expect? If I take this point up by x, will it going to go up by x or not? Your physics brain is working over here. You would say that no, it is not going to go up by x, it is going to go up by less amount, because as you pull this up, this thing is going to rotate and go up, and the same movement is not provided to this. Now that is by intuition, and then you'll analyze that what is happening over here. So now the best is to move this movable pulley in a direction which is going to loosen up all the strings. So what you can imagine is you have laid all this down on a table and there's no gravity and all. All the strings have to be tight. So if you lay down on a table and move the pulley up, so we'll concentrate on the center point of the pulley. So it was here earlier, now it is here. So you have moved the pulley up by say, since I said x for that, let me write it as a. So if you have moved the pulley up by a, what has happened now? So we'll analyze what has happened now. The thing is, this body 1 was directly attached to the center of the pulley. So if the center of the pulley goes up by a, then this also will go up by a. So this movement is straight. It's a straight constraint. It is directly attached to the body. So whatever is the movement of the pulley is the movement of the body. So the body goes up by a. Now what happens to the string? What we see is, this was your string. Earlier we have not moved this part, we have laid it down on the ground, and we are just seeing that what is happening in the new position. Your body 1 has gone up by A amount. So now it is up to us to pull this part of the string to make it again tight on the pulley. Now this part is overhanging. So when it becomes tight on the pulley, then whatever was the curved part will again come back on the curve. What was the loose string which was hanging is so much and so much. So you have loose string this side as well as this side which is overhanging. That's your loose string. This is the loose string which is overhanging, and this is going to become tight. So how much you have to pull this side so that this loose string and this loose string is tightened again. So how much is that amount? This loose string is A here and A here. So what you have to pull up by is 2A. You have to pull this point up by 2A so that the loose string again becomes tight. So that is how you do by inspection. You move the movable pulley in a way such that the strings become loose, and then you tighten the string with your own hand. While you are moving the movable pulley, the things which will not move automatically, like this body and all, will move automatically. The things which will not move, it is not bound to move automatically, just stay them put at where they were, and just move the movable pulley, see where the strings have gone loose, and then tighten those strings. Pull one by one and tighten those strings. So if you pull this by 2A, then your A and A is going to get the loose string A and A is again going to become tight, and eventually the body is over here 2A. So going back to the original question, if this has moved by X and this has moved by Y, then the relation is X is equal to twice of Y. X is your 2A and Y was your A. So whichever movement is asked, whether the body was asked to be pulled down or pulled up, it will not matter. If the body had gone down by A amount, this point would have gone down by 2A amount. So in the initial question, whether it is that the body is going down or going up, you are going to work to make the strings loose, because that comes more easily to the mind. If the strings are loose, then you are able to understand the situation, analyze the situation better. So eventually this question would have been something like this. So we have analyzed the movement of this point. So when this is going up by A, this point is going up by 2A. This is a fixed pulley. So if this point goes up by 2A, a point over here is going to go down by 2A. Eventually the body is going to go down by 2A. So what we are seeing is, in a fixed pulley case, as the earlier case, the movement on one side is equal to the movement on the other side. But when there is a movable pulley, it's dicey. You have to see what is actually happening. So generally, if it is one movable pulley, you will have a factor of 2. Like if the movable pulley moves by X, then the point on the other side is going to move by 2X, provided this side was fixed. You can think of a knot tied on this and think what happens to the knot while you are pulling this point up. What happens to the knot? The knot remains over there because this length remains the same. This point is attached to the wall, so the knot is also going to remain there. So whatever part of the string you watch over here is going to remain there itself, and all these strings which have to be pulled up has to be pulled up on the same side. So if I had to solve this question, my preferred method over here would be analysis. I will identify where the movable pulley is. I will lay everything on the ground such that there is no effect of gravity or anything. I know all the strings are going to be tight. I am going to move the movable pulley in a way, in a direction which loosens the strings, and I am going to tighten the string again. So when I move the movable pulley up by X, I get X and X, 2X loose string. So to tighten the 2X loose strings, I have to pull this thing down by 2X so that the whole loose string, this blue loose string, gets tightened and this loose string comes back on that thing. So that is my analysis way. That's the preferred way for me over here. The other way would be, as I have said earlier, this is one string. We can just watch on the lengths of the string. So one way is mark all the lengths from the ceiling to the pulley, the initial length, and then from here to there. Okay, I'll quickly mark it, but I'm not going to do this way in any given case. I'm not going to do this way what I'm going to show you right now in any given case, but still, to get a feel of the whole length of the string and everything and how it is going, I'm just going to mark it. Say this part is A, this part is B, and this part is C, and the lengths over the pulley is same. So this is the orange string which I'm counting on. Later on, the string is this black one. Pulley has gone up, gone up, gone up. So the body has come up. So this string would have gone down. So this is the black situation is the later on situation. Now, if this pulley has gone up by X and this thing has gone down by Y, so I'll just write the total length again. So the total length on this side would be A minus X. A was the initial length, but it has gone up. So this is your length now, which is your A minus X. What about this? This was your B. It has gone up over here. So this length becomes B minus X. So this length is your B minus X. And what about this side? So we'll not call it as 2x yet because we have not found out what's the relation. So we'll call this side as this extra length is your Y over here. This was your C. So this is your C plus Y. So that's your total length of the string. And in the blue case or in the orange case, in fact, earlier the total length of the string was A plus B plus C. So you can rewind and watch before I had drawn this black rope. The length of the string was A plus B plus C. So it must be equal to A plus B plus C. So what we see over here is A, B and C gets cancelled. You get minus 2x plus y is equal to 0 or y is equal to 2x. So here marking the whole length was not necessary. So improvised version of the same thing would be, again I'll redraw for you. One thing you may notice, I'm just concentrating on the movement of the pulley. I'm not talking about this mass moving, because I know how much ever this pulley moves, that mass moves that much. So you may look out for such setups where the mass is attached to the center of the pulley. So where how much ever the pulley moves, that much is how much will the mass move. Now, if this pulley has gone up by X amount and this has gone down, this body has gone down by Y amount, then what can I say about this section of the length? This section of the length has reduced this section of the length. One coming from the pulley to the attached point. This section would have reduced by X. So reduced by X, whatever minus X. So that whatever, by the way, was A. And the here whatever was your B, and the here whatever was your C. So whatever minus X, and whatever was the length earlier, that length has also reduced by X. The top point has remained where it was, but the bottom point has come up by X in the new situation. So minus X. And here this section of the rope, this point is here itself, and this would have gone down by Y. So whatever length, that was a C plus Y. So this is what we are talking, minus X plus Y. So the total reduced length must be the total increased length. So if we write like this, so it is equal to 0, what we get is Y is equal to 2x. So I think this is much faster than drawing all the lengths. In fact, in many a case, you need not draw the pulley again. So one is intuition. I'll prefer intuition over here. I take the pulley up by X. I get a loose string over here. Of X and X 2x. So I have to tighten this part by 2x to make the string tight again. Why am I saying that I prefer this method? Because I'm more closer to physics when I'm thinking of all these things. When I just write minus X plus Y and all, that time I am more into mathematics, but I'm not getting into the feel of the question. So I would prefer the first method. Now, so my methods were, one is analyze. Method 2 is, so I've listed down 2 methods. I'll do one more method for this setup. So first method was analyze, and that is by inspection you find out. I move the movable pulley one. And the next method is you write the increase and decrease in the length of each section of the string and equate it to 0. How much each section of the string, so these were 3 sections in the string. 1, 2, and 3. This section has decreased by how much? This section has decreased by how much? And this section has increased by how much? So that was your decrease, decrease, and increase, and equate it to 0, and you'll get the constraint relation between the movement of the two ends over here, provided all the strings are tight. So one more method over here is related to work. So that will require a bit of knowledge of forces and work. So anyhow, I guess you would be knowing that much. So let me show you over here. This is a clean area. Whether this was a body or this was a point which I was going to pull down, and this point is going to go up, or this is a point which I'm going to, in this case it is made like y pull down. So this is going up by y. So if I had put a force on this, say I had put F force on this and has gone down by Y amount. So what is the work input by me? How much I have done work on this by this force? The force has done a work of F into Y. Now in any machine, whatever is the input work in has to be equal to work out, or input work is greater than work out. Input work is greater than equal to work output. Output work cannot exceed the input work. So efficiency can't go more than 100%. Now if I have to find the relation between the movement of the two bodies, then whether this pulley was having a lot of friction, whether it was an ideal situation or not, it was creaking when I am moving it, when I move it, but ultimately when I move this Y down, it has to go the same X amount up, whether it was having a lot of friction over here, or there was no friction. So if I have managed to move it Y down, this has to go X, which is equal to Y, up in this case if I have managed to move it Y down, and this string is not extending, it is inextensible. So the point is, whether the pulley was ideal or not, I can change the situation to ideal situation, and I'll say if it was ideal pulley, and if it was ideal pulley, then there is no loss of work in the frictions, in overcoming the friction here, in the friction over there, and say the string was having no weight, so there is no loss of work anywhere. So the only work which is getting input and output is these endpoints. So whatever I have inputted the work, that much output must be there. Now we also know by the third law of motion that if I pull a string down by F, the string is going to pull me up by the same amount F. So your T is equal to F. If the string is massless, then this T is going to get transmitted with the same value. This T is not going to reduce. So what I'm doing is I'm just changing the whole situation to an ideal situation. Now here in these cases, when I said it, I never mentioned that these are ideal pulleys, means having no weight and there's no friction and all. There could have been friction, there could have been weight of the pulley, but still whatever has been discussed earlier remains the same. The only thing is the string was not extensible. The string could have got a mass also, but it was not extensible. Now if I have to do it by work, I just imagine that everything is ideal. So whatever is the work input is a work output. So what is the work input over here? F into Y. That's your work input, F into Y. What's the work output? So what we see is the tension has done the work over here. Tension into Y or X is the work output. That was your X. So the work output is tension into X. They would be equal if it is ideal situation. And by third law of motion, F is equal to T. F is equal to T. So F and T cancels. What you get is Y is equal to X. So that is obviously much ado about nothing. This question is having no great analysis is required to figure out that if this goes up by X, this is going to go down by Y. But what I'm trying to emphasize over here is we can use work to get the restraint in this situation and all these situations. So what we have done for ICSE guys would be knowing it. What we have done is we have taken an efficiency case of 100%, and then we know that velocity ratio is going to be equal to mechanical advantage. Velocity ratio is movement of the effort, distance moved by the effort divided by distance moved by the load is your velocity ratio, and mechanical advantage is your load divided by how much effort you apply. So effort is where you are putting in the work, E times dE. This is the work input, and load times dl is the work out. So in an ideal situation of 100% efficiency, VR is equal to MA. So that is what we are going to analyze. So whether this machine was ideal or not, it was all greased up or not, we know that the constraints are going to remain same. So even if the machine was not ideal, we make it ideal. We make it ideal means we put all the pulley weights and everything as 1 and no friction, and then do it through work. So if I do this question through work, method number 3, on this question if I apply work, let's see what happens. You also try to write an equation. So where are the input ends and the output ends? You can consider any one as the input work end and the output work end. So I'll tell you one thing to do where you don't have to bother about the input and output work end. So here F is down and the body goes down. So we said a work of Fy, positive Fy is done. Here the tension is up and the body goes up, so a positive work of Tx was done. I'll just clear this area. So there was a positive work of F into Y because the force direction was downwards and the movement direction was downward. And there was a positive work of T into X because your X was upwards and the force was also upwards, the tension was upwards. Now if I see what is the work done by this tension on this body or on this point, then what is the work done? Tension is upwards but the point is going downwards by Y. So what is the work done by the tension? The work done by this tension is T into Y but negative because tension was upwards but the thing has gone downwards. So T into Y negative is the tension, is the work done by the tension. The work done by the tension all over. What's the work done by the tension over here? T into no movement of this point, T into no movement of that point. What is the work done by the tension over here? Work done by the tension over here is T into X. So if we add up all the work done by all the tensions, we add up all the work done by the tensions, we get the total work done by tension is 0. So one explanation can be this: your F and T were vectorly opposite, your F magnitude was equal to T magnitude. So what I said over here, you can apply that and think of why total work done by tension will be equal to 0. You can say that the tension is an internal force. Internal force acts on both ends of the string. The tension acts, it pulls both the ends of the any section of the string, as you see drawn over here also. So that's the internal force. Now if this string is going to be tight all the time, then if this part moves this side by x, then that part is going to move that side by x. So the work done over here will be a positive Tx because T in the direction of the movement, but here the work done will be negative Tx because T is this way while the movement is that way. So the movement has to be that way because the string is tight. So if the string is tight, we can analyze any two ends of the string and say that the work done on one side is equal and opposite to the work done on the other side. So positive Tx this side and negative Tx this side. So total work done is always going to be 0. So this becomes another method to do this question. So that's all theory. We'll apply that method over here and then we'll understand. Remember, take it as ideal. Even if I give you weight of pulley and all, make it as a 0 mass pulley and do it. So give yourself a minute and do it while I redraw the question. So that's your question. Let me draw the tensions in front of you. Tensions in any section of the string pulls both the ends of the string. So the tension over here, it's pulling the wall by say T amount. Other end is pulling the pulley up by T amount. This section again will pull both the ends. It's the same string which is going, so TT. This section again will pull both the ends, TT. Now if this pulley is massless, then what we can say is this T in this part of the string or this section is equal to the tension in this section is 2T. Now why do we say that? Say it was T dash. We make the free body diagram of the pulley. Now this is off the topic, but I'm just making it over here because I've seen students making mistake over here. So two tensions were pulling it up and the tension down was T dash, and suppose we don't agree that it is twice of T, we have made a free body diagram of this. We'll write an equation for movement of this. Say the pulley was going up with a certain acceleration A. If there's a residual force on it, there's a certain acceleration produced, which is say A. So if the body is going up, then what we can say is all upward force T plus T minus the downward force T dash must be the mass of the pulley into acceleration of the pulley. If this mass is considered to be 0, what we can write is 2T minus T dash is equal to 0. Hence we say take T dash as 2T. So this T dash becomes 2T only if the mass of the pulley is 0. So now what I said, even if there is mass, the constraints would be same, but you consider the mass to be 0. So therefore I was emphasizing on that. Now these are the two ends where you can write the work, and all other ends you may ignore writing, because whatever tension is pulling whatever thing, if you considering any other concept not applicable over here. So what we are going to concentrate, as explained earlier, is the input and the output point. So here if I'm going to pull it down, this is going to go up. So the input work will be my force downwards into the movement down, but in that case I have to write input is equal to output. The other format of the same thing is the total work done by tension is equal to 0. So we'll concentrate on the work done by tension at the input point and the output point, not the work done by me, not the input work done, but the work done by tension at the input point. So let's see what were we doing earlier, that this point is going up. Okay, so this goes up by say X amount and this comes down by say Y amount, and we don't know the relation yet between your X and Y. So what we can write is the work done by tension over here is 2T. 2T was upwards on that point and it has gone upwards, so it is a positive 2T. The work done over here by the tension on this point is, the tension was upward but the point went down by Y, so it is minus Ty, and the net work done has to be 0. The T's get cancelled and what we get is 2x is equal to Y. So that's again the same relation what we were getting earlier. Here I'd called this as Y, so that was the other way around. Here I'm calling this as X and this as Y. So this has gone down twice the amount of how much it has come up. So again a very useful way, but not required in this particular case. But many cases you'll find this work done method quite useful. So I'll write down our method 3. Total work done by tension is 0. So going by these methods, you'll be able to pretty much solve most of the questions. So even if you are getting it through the mathematical methods like 2 and 3, try to analyze how the things are moving and verify in your head that whatever you are getting through the method is aligned to what you have analyzed. So let us take up some problems of more worth now. Now before we go on to solve a question, let us just add one more option to our preferred methods, one more tool in our kitty, particularly helpful when there are more than two bodies moving. So say this looks very odd, so I'll just draw a point over here. Say this is going up with a certain velocity, this point is 1, this point is 2, this point is 3. So this is going up with V1, this is going say up with V3, and this is going up with V2. Say all of them are going up with a certain velocity. It could have been going down or any other way. Now these are the velocities with respect to ground. V1 with respect to ground, V2 with respect to ground, V3 with respect to ground. But we very well know that there is a relation between V2 and V3, particularly when we see with respect to the pulley. With respect to the pulley, how much ever it has come up, that much it must be going down. So the velocity with respect to the pulley was, suppose u up over here, then with respect to the pulley it is u down this side. So velocity of 2 with respect to the pulley is equal to velocity of 3 with respect to the pulley. So this is, one is upwards and one is downwards. So one is negative of the other. What I'm planning is to use our known equations in relative motion over here. What do we write velocity of 2 with respect to the pulley as? We write velocity of 2 with respect to the pulley as v2 minus velocity of the pulley. So that v1 is your velocity of the pulley. So I'll rather write vp over there, is equal to negative of velocity of 3 with respect to the pulley. Velocity of 3 with respect to the pulley is v3 minus v pulley again. So what do we get over here? What we get over here is v2 minus vp is equal to minus v3 plus vp. If we rearrange and write, we'll get velocity of pulley is equal to v2 plus v3 divided by 2. This goes on the other side, that goes on this side. So this is an important relation. What we are getting over here is, and since all of them are in straight lines, so this is a vector equation. So I've taken everything up, up, up. So v2 up, v3 up, by 2 is vp. So this was, say, going with 2 meter per second up, and this was going with 4 meter per second up. Then the pulley must be going up with 3 meter per second. If this was going up with, say, 2 meter per second, and this body was also going up with 2 meter per second, meaning to say both were, this length of the string is not increasing and both are going up with the same velocity, then the pulley must be going up with the same velocity too, and there's no movement, there's no relative movement between these two parts. So if this is 2, this is 2, this must be 2. So that is what our equation gives, 2 plus 2 by 2, which is 2. If this was 4 and this was 2, then the pulley must be going up with some average speed of 4 and 2, which is 3. The pulley must be going up. Then only it can accommodate this also going up, that also going up, with the string being tight. So for our convenience, I have written everything in one direction. So let us just apply this in one or two more situations. If I say this point is going up by 2 meter per second, this point is going down with 3 meter per second, find the velocity of this point. So this point is going which way, up or down, and with what speed? So we'll simply apply the formula over here and we'll check it through our analysis thing. So what we write is the pulley, say, upward is all positive. So because this is a vector equation, so we'll have to take positives and negatives. So remember, all of this is happening in a vertical line, in the same line. So it is quite, this formula becomes quite easy to apply, only plus and minus here and there. So 2, say, upwards, so velocity of the pulley is 2. Velocity of this body 2 is downwards. This was up, which was considered as positive, so down is negative, so downward will be minus 3 plus whatever velocity we have to find. If it comes positive, then it is upwards. If it comes negative, then it is downwards, divided by 2. Before calculation, before going to look into the math, what do you think? This body will be going up or going down? Analyze a bit and tell me. So to analyze, what I think, what I do is I make things stationary. If the pulley was stationary and this body is going down with 3, then it was going up with 3. So give me a big hint that it might be going up with 3. And plus this 3 is a larger number than 2, then maybe the 2 is, whichever way it affects, it is not going to affect the 3. So it gives me a hint it must be going up. Anyways, if this is stationary, this is going down with 3, it goes up with 3. If this was stationary, this block was stationary, and the pulley is going up with 2, what will happen to this? If this block was stationary and the pulley is going up with 2, this will still go up. So both the movements, the body going up as well as this thing going down, causes this thing to go up. So my guess is it is going to go up more than 3. I'm not even guessing, I'm not only guessing that it is going to go up, I'm guessing that the value is going to come more than 3, because if this was not moving, if the pulley was not moving, this alone 3 movement down would have caused a 3 movement up. And the pulley moving up is going to make it move up even more. If the pulley had gone down, then the string over here would have become slack and this would have gone down. Then it could have been debated what is happening. So over here, what we calculate and what we see is, you'll have your V is equal to 4 plus 3, which is 7, which is what we guessed. So our analytical mind is saying, yeah, we should get a big number, we should get an upward big number. So that is your 7 meter per second. So take a pause and analyze this thing, why we should get a big number upwards. Don't concentrate on just applying the formula. Concentrate, consciously get yourself involved with how the bodies are moving, analyze what is happening, and you'll be more close to solving questions if you have that kind of analysis. Say the pulley was going down, and say it was going down with 2 itself. So I'll just change the question, it is going down with 2. So this over here becomes minus 2. So I'll redo the question this side. So the pulley is going down this time, minus 2 is equal to minus 3, this is going down, plus V by 2. Now my guess is this going down is going to make this go down. This body going down is going to make this go up. Now who is going to win? My guess is the pulley downward movement, which is going to make this which will make this going down, is going to win over this downward movement, which is going to make the body go up. Now why that? Because a certain movement in the pulley, say x in the pulley, gives you a movement of 2x over here had this not been moving. If this is stationary, again I'll apply the same principle. I'll make this stationary and just move this and see. So if it goes down with 2, it is going to make it go down with 4. Now since it has gone down with 4, this pulley have to make it go down with 3, so it is going to pull it up by 3 back, because that's a direct link. So 4 minus 3, I should get it as 1. Let's see what we get. So what we get over here is 2 into 2 is minus 4 over there, and 4 comes this side, so it is 1. So we get, in mathematically we get V is equal to minus 1. So mine upward was our positive direction, downward is negative direction, so we get 1 downwards, 1 meter per second downwards. So that is what we have done through analysis also. So this formula is a safe formula, but do try to analyze also. So I'll just repeat the analysis over here. Pulley going down with 2, this going down with 3. Now even if it is accelerations, the ratios will be same. Even if it is displacement, the ratio will be same. So it is 2 meter per second in this case, that's the velocity, and this velocity is 3. So I had guessed that this will be going down. The reason was, if I don't make this body move and I make this body stay put over there, and I move the pulley down with a certain amount, it goes down with say 2. So this body remaining over there will make the string tight by moving this down by 2 plus 2, which is 4. If this is x and x, this would be 2x. It has to go down by 2x because he had caused a loose string over here of x and x. Now once the body is over here, I realize the pulley has made its movement. The pulley is down by 2. The pulley is over here now. So we are done with its movement. In 1 second it is down over here. But then they said that in 1 second this body had to be down by 3. The velocity with respect to ground was 3. So I'll make this go down by 3. If I make this go down by 3, this has to come up by 3. So it has gone down by 4, comes up by 3, goes down by 4. So ultimately it is down by 1. So think over it. So in the analysis part, I forgot to mention over here, if there are too many moving parts, you make them move one by one. So we'll do that when we take up the questions. So this becomes a tool for you. If two things are overhanging a pulley, then we can say velocity of pulley is equal to velocity of, say, body 1 plus velocity of body 2 are the two bodies overhanging the pulley on two sides divided by 2 in a vector situation, in a vector equation. So that's your VP, that's your V1 up and V2 up, all same direction. That's vector in one direction, this is the vector equation. So that becomes a tool for you. You can use this also when required, but don't forget to analyze what is happening.